Hello everyone, welcome to another physical science lesson. We're getting into relationships and we're going to be talking today about how to represent relationships. Now I'm not talking about drawing hearts and carvings on trees or anything like that, or writing little notes or sending messages. No, we're talking about real relationships, the relationships that you'll find in physics. So let's go and have a look at them. So if you remember, we're talking about relationships. There are different types of relationships in physics and in chemistry, and we can classify these in terms of the most important one, the most useful one, is a directly proportional relationship. We've also spoken about something that is inversely proportional. We haven't really mentioned the squared relationship. We're going to talk about that today, but the critical focus is how we represent these. Now, relationships can be represented in words, tables, and graphs. Today, we're going to focus on this relationship, the relationship between graphs and equations. And so you might have wondered, where do things come from when we're dealing with our physical science textbooks? We'll see suddenly an equation pops up or a graph is drawn. What's the link between the things that we observe, the data that we look at in an experiment, the graph that we draw, and the equation that we use to solve problems? Well, that's exactly the question we're wanting to ask. How do scientists link graphs of data to an equation? Well, hopefully by the end of this lesson, you'll be able to answer that you know exactly how we're going to do it. So let's focus and let's get together our initial terminology, things that we've learned of before, and things that you're going to need to remember as we go through this section. And in fact, all sections of physics and chemistry. So the first thing that I want to talk about is just quickly recap this word directly proportional. I said earlier it's the most important relationship, and you would remember that when something is directly proportional, we have two variables. Let's just take, for example, A, and we say it's directly proportional to F. Then that's the way, the notation that we're going to write it. We also remember that if you were to draw a graph of A against F, then what you're going to do is you're going to see that this graph is a straight line graph that passes through the origin. The independent variable is the one that you choose to control. It's this force that we're going to be controlling here, and the acceleration for A is the dependent variable. It's the outcome, the result of you applying a force to an object. So please bear in mind these factors as we're looking at graphs and we're thinking about relationships. Which one are we controlling? Which one is a result of the experiment that we've set up? Now, what's so nice about the directly proportional relationship is it's very easy to go from the graph to an equation. And we're going to show you exactly how that works. So let's take a very simple example that everyone is familiar with, an object moving at constant speed. Now, when an object moves at constant speed, I'm going to just illustrate what that looks like. If that's the starting point, so that's the initial point where we're going to start the clock and we're going to say time equals 1, then after a certain amount of time, what we're going to find is the object has moved. That's time equals 2. In the same time interval, we'd find that there's moved an equal distance. So if we were to compare these distances that have been moved, you'll see they're roughly equal. In each of the time intervals, we'll find we have equal distance in equal time. And so what does that mean for the graph? Have a look carefully at what it means for the graph. And I want you to watch this very carefully because it's very important. In each time interval, time intervals, remember, are the same. You're going to see that the distance that is increasing is the same. So if I were to say that was T1, let's call that T2. And I'm doing this quite roughly. But you'll see that the object has moved a certain distance. The distance that it moves, I'm indicating with the blue arrow there. Now, if I went a further distance, I went from T2 on the graph to T3. There's my T3. I'm going to do the dots up like that. And you will be able to compare, even though I've done it very roughly, that distance is about the same. So in equal time, it's gone the same distance. And so we could carry this process on. What that is meaning is that we're going at a constant speed. We're not speeding up. We're not slowing down. We're going at the same speed throughout the measured time. Okay, now, having got that idea, let's have a look at the graph from a mathematical point of view. What are the features of this graph mathematically? Well, the first thing that you'll notice is it's a straight line. It has a certain steepness. We call that steepness the gradient. And the gradient at this position, and the gradient at that position, and the gradient at that position is all the same. It's a constant. Now, remember how we work out gradient as well. We can take gradient and we can say it's the change in distance over the change in time. In effect, it was what we've just done previously by seeing it was the same. We can say, what was the change in time over the change in distance? Change in distance over here, and the change in time over there. And for whatever number of triangles we want to draw, these will come up to be exactly the same because it has a constant gradient. Now, the second feature of this graph is that it intercepts at the point 0, 0. In this case, it cuts the y-axis and the x-axis at 0, 0. So this is a special line function or a line graph, and we need to take a note of the form that it forms. All line graphs have this generic form, y equals mx plus c, where the y stands for the dependent variable, where the x stands for the independent, the c stands for the intercept, and the m stands for the gradient. Now we can see here the gradient is constant. We recognize this c is going to be 0. So when we put this all together to try and make an equation that relates distance and time, it shouldn't be too difficult to see how we're going to do that. To make it look like this sort of an equation, the first thing we recognize is we've got the gradient. The gradient, the m bit, is actually just the ratio between distance and time. Because this is a constant, we can say the distance is directly proportional to time. If we go to the equation now, we can see that there we've got distance divided by time is a constant. If we double the distance, we have to double the time. If we multiply the distance by a half, we have to multiply the time by a half. This isn't in the form of yx plus c. It's just in the form of a constant gradient. It's in the form where we're showing the gradient is the change in y over the change in x. But we can unwrap that. We can multiply through some things, and we can get distance on its own. So we're going to say, let's make distance, which was the dependent variable, is equal to the speed, which is the constant. This is the constant. And there's your time. And so if you compare these, you'll see that relates to the y, that relates to the x, the c is 0, and this is your gradient. How cool is that? Just by looking at a graph, we can establish an equation. Now, I want you to think about it very carefully while you take a short break. We'll be back straight after that.